of the RNS string theory. Okay. So remember, the idea was that we had lots of fun doing the bosonic string. We quantized the string. We found that it was actually remarkable that from the beginning, when we did the bosonic string, we could have realized that there would be trouble put the indices. Just from day one, when we wrote down this action with the Minkowski metric here, we knew that you could have complained and said immediately that this quantum field theory would not make any sense because there will be scalar fields that will have the wrong sign for the kinetic terms, right? And indeed, well, you didn't ask and I didn't tell you. We just kept going. And we paid a price when we tried to quantize the theory. And we realized that indeed, now we know why we don't do that in quantum field theory usually, right? Because we will have states with negative norms, right? So indeed, this quantum field theory, just as it is here, just as written, has states with negative norm. So that was correct. It was our expectation, or it should have been our expectation from day one, and we ended up facing a problem. But of course, this is not the quantum field theory that we wanted to study, right? We had to supplement this by constraints. Once the constraints were imposed, miraculously, we ended up with a spectrum that was reasonable, okay? And the way we did it was going to this Lycon gauge quantization, which was a trick. The trick, of course, once again, made something manifest and made something that was not made something that we wanted, not manifest. So the thing that was made manifest was unitarity. We were able to get rid of all these negative norm states. And the thing that was not manifest was Lorentz invariance in this configuration space of this theory. So what other name did we give to the configuration space of this theory? By configuration space, I mean the space of possible values of our fields here. How do we call that? Yes? Coordinate space or space-time. Our space-time happens to be the configuration space of this theory. Okay? Well, it was something like this. If we set alpha prime to 1, there would be something like this. And then we said, OK, fine. Everything works out fine. Of course, we also found that in order to preserve Lorentz invariance, which was a global symmetry already in this theory, to preserve Lorentz invariance at the quantum level, at the same time as unitarity, we found that the number of fields had to be restricted to be 26. Okay? The theory was smart enough to tell us that both things could only coexist when D was equal to 26. Okay? So that was very good. We found that the theory in the spectrum has states that could become gravitons. So this theory could actually be a theory of quantum gravity, but not something that describes nature, right? First of all, it's in 26 dimensions. We said we would not worry about that. But another problem that was more important was that we didn't have fermions. So the first attempt would be to add to this fermions. You want fermions? Well, just add fermions. So we just added fermions, once again, exactly with the same structure. Now, is there any other way we could have done that? Well, you could have said, maybe, one way to have fermions following the same spirit of the original construction would be to say that in space-time, at the same time as having bosonic coordinates, maybe you could also have fermionic coordinates in space-time. Who says that the coordinates, or what we call space, has to be all bosonic? Well, that's what we seem to observe. But even if there were fermionic directions, they would have 0 dimension, because remember, fermions, we have to satisfy these Grassmann algebras, so they could not be something that we see macroscopically. So perhaps there are also fermionic directions in space-time. And mathematicians have studied things like that, so they are called supermanifolds. So perhaps another approach we have been to consider another approach we have been to consider, in addition to space-time directions that are bosonic, to also include fermionic space-time directions. Okay? Well, this is an approach that Green and Schwarz followed, and it's called the Green-Schwarz formalism. Okay? In this case, you have a supermanifold, which is your target space, and then the action for the stream moving in that space-time is the induced metric on that superspace. Okay? But we're not going to follow this approach. We will stick to our RNS formalism. But I would like to encourage you, if you are curious about this, to go and study this formalism. In particular, because there are some things that are easier in this formalism that are hard in this one. Okay?
So is there the same number of fermionic directions as there is of the bosonic directions in this formula?
Well, depending on the number of fermionic directions, will change the number of supersymmetries you have, and the theory behaves differently. In fact, the number of space-time directions will also change. There is one value for which the actual critical dimension happens to be 4. You say, why isn't that what we're doing? Well, because it turns out that the signature is also fixed for consistency. Has to be 2,2, cannot be 3,1. Just almost. Okay. Well, in any case, so we did lots of things with this RNS model, right? So one of the things we did was to say, well, these guys are actually Majorana vibe. Okay? So we could decompose them into psi plus and psi minus components. In terms of those, the action ended up being something that looks like something very, very simple. The plus and minuses actually told us that this thing really wants to be written in the coordinates d sigma plus, d sigma minus. Right? We said that last time, that the action, the form of these guys was begging you to choose these coordinates. Okay? We found the field equations, which were simply telling us that these guys can only depend on sigma minus, and that these guys can only depend on sigma plus. We also did boundary conditions, and that's the reason for the name RNS. We decided to study the open string. And the boundary conditions we found two kinds of boundary conditions for the fermions. One of them was called R. The other one, let's see, was the NS. It was R because it was found by Ramon. And the boundary condition was that our fields remember, this condition was the same for the both sectors. Okay. And the one that was different was what happens at pi. And the one that was studied by Ramon was to choose a plus sign here. And the one studied by Naviu and Schwartz was to put a minus sign here. Okay? So it's something we didn't do last time, but I asked you to do, was to find the mode decomposition of these fields consistent with the boundary conditions. So we have something like this. Remember, this guy only depends on sigma plus. So we can just go directly and write it as a function of sigma plus. So we will have something like, there is a square root of 2, which I'm going to write now, but I'll purposely, in fact, well, if I'm not going to write it anymore, why do it the first time? You will get into the habit that I have to get all the factors correctly. That shouldn't be. So there are some normalizations that we can put there. And the oscillator modes in this sector are usually called D. Okay. Now for these guys, in principle, we can have some other oscillators. Okay, D prime. But these conditions imply, so the boundary conditions are satisfied if we choose, only if we choose these oscillators to be the same. Okay? There is something else. Remember, we said that these objects, these fermions are Majorana. Okay? And being Majorana means that they are real in the proper sense. And in order to impose that condition, we have to impose that the mu dagger is the same as so that will come later on. When we interpret these as quantum operators, we will have to remember these conditions that came from the fact that they were Majorana. Okay? So now let's do the Naviu-Schwartz. So this one is slightly more interesting to get right. These ones are usually called B. Okay. So now, from this condition implies is that BR mu and BR prime mu, they will have to be the same. Okay. Now, once we know that they are the same, we can try to impose this condition. So let's impose this condition. How do we do that? So the way we're going to do it is to say at sigma equals to pi, let's add up both equations. So let's compute this. Okay. Well, the boundary condition tells us that if we add the map at pi, we should get 0, right? So the boundary condition is that we should get 0. Now if you look on this side, after using that B and B prime are the same, we just combine these two formulas, and we get that the sum, we should get the sum over R, BR mu, e to the I, sorry, there is an R here, right? Somebody should have told me this was an R. Right? We are summing over R, there was no n. You see, that's the way I can tell. I did it on purpose to see how many of you were awake. See that not many people are. So let's split sigma plus and sigma minus, remember, in tau plus minus sigma. Let's put it here. Let's take the sum and write it explicitly. They both pick up the same factor of e to the minus IR tau. And the rest will combine into cosine of tau, sorry, of sigma n sigma, sorry, R sigma. Okay? And we need this to be 0 for any oscillator modes, and therefore this implies that R better be a half integer. Yes.
Shouldn't we have a factor of 2? Anyway, let's see.
The argument of the cos should be cos R pi.
Sorry?
The argument of the cosine should be R pi.
Yes. Okay, so I think it's working, yeah. Now you're awake. That's good.
Why R pi sigma?
Sorry. Even better, yeah. Now I'm the one who's asleep. So now we're trading. Okay, very good, very good. Excellent. Okay. Now we know what these guys are, so we should put R that belongs to Z plus a half, and R that belongs to Z plus a half. And there is no prime here, so those are our modes here, and those are our modes here. We can remove this prime from here. All right, very good. So what do we want to do next? Well, the natural step is to attempt a quantization of the system, right? That's exactly what we did next in the bosonic case, right? We wrote down the modus functions satisfying the boundary conditions, and then we tried to quantize.
What has a similar real condition to it?
Sorry?
A similar real condition as which we get for the London's.
Oh, yes, yes. This condition, you mean? Yeah, so in that case, we also get a reality condition. So we also have a reality condition. Okay, so now let's try our quantization of the system. Now, in this case, the quantization proceeds by taking the classical relation between the fields that was 0 and turning this into a quantum relation. Now, following exactly the same steps as you guys did in the bosonic case, we will end up, well, first of all, remember, this theory has bosons and fermions. Okay, so the action is the sum of these two actions. So we are not only considering the fermions, we're also considering the bosons. So we have to remember to keep track of everything we did for the alpha oscillators. So let's just write it here to keep it in mind. But when we do the same thing for the fermionic oscillators, I wonder if we could try to do it. So for the fermionic oscillators in the Ramon sector, we will have dm here we'll have, so that's what we're going to get there. And here in the NSS and Navier-Short sector, we will get something of the form do you notice any difference between the anti-commutators of B's and D's and the commutators in the alphas? Do you think I forgot something in this case that I didn't forget here? Well, I thought you were going to say the M. Right here, these guys had this funny M sitting there, right? Here, these guys don't have it. I didn't make a mistake, just to tell you. It's not a type. So why do we have these guys here and not here? Can you trace that back to something that is on the blackboard?
The expression of quantitative derivative.
Exactly. Right. Look, this guy doesn't have a derivative. And that comes from the fact that the fermionic action has only one derivative. Right? So the canonical conjugate variable to psi is this guy itself. Well, in the other case, we had x and derivative of x. Okay? That's the source of this M. Here we get just these guys completely clean. So that's very good. Now, how about the Hilbert space? So we're doing quantization there. We're also doing quantization here. I mean, somehow we're having that side of the blackboard to be the NS sector and this one to be the R sector. Let's see if we can keep the convention. So we have to study the Hilbert space there and the Hilbert space here. Okay. First of all, yes.
So is it possible to have strings in the R sector, in the NS sector, in one theory at the same time, or do you have to decide at the beginning which of the boundary conditions you use?
Yeah, we have to set from the beginning what boundary conditions we use. Yeah. Well, the reason is that you may ask, well, can I impose some boundary conditions for some mu's and some other boundary conditions for some other mu's, right? Well, what do you break if you do that?
Lorentz invariant.
No. Well, but we know already it's more or less the same question as the Dirichlet and the Neumann boundary conditions, right? So we said the only reason we don't impose both is that we also break Lorentz invariant, right? But well, in the case of the bosonic string, or in general, we will also find that well, sometimes you want to break Lorentz invariant. And just preserve it on a 3+1 dimensional subspace. Yes.
Why did we end up with anti-commutators?
Because we started out with anti-commutators. Yeah. And you remember why we need anti-commutators if you're dealing with fermions, right? That goes back to your quantum field theory course, right? Otherwise, the Hamiltonian will have a funny property. Do you remember? Yes. Oh.
Just a question. So is this anti-commutator between psi plus and psi minus?
No. These are the psi's. These are the ones on top, the Dirac ones, if you wish. Okay. Okay. So how about the Hilbert space? Well, first of all, we should try to see if we're going to have the same problem as we did before, right? Negative norm states. So consider a state of the form. Let's do it here first. consider a state of the form dr acting on the vacuum. Now we'll have to put a name, ns. This is a vacuum in the ns sector. And let's put a 0 here. Okay? What do you think? Is it going to have negative norm or not? Who thinks it's going to have negative norm? Only one person. What?
I don't know.
Okay. You think that it will have negative norm or not? Okay, 2. Okay. Well, how can we tell? Well, we compute the norm. Well, of course, I know. I didn't tell you. So, yeah. So we have to take R to be positive, right? If you take R to be positive, this will be dagger here. Okay? Or we can take R to be negative, and it will be fine too, right? But whatever we choose, when we compute this guy, okay? So we get this thing. And the only difference from the bosonic case is that we will have to apply an anti-commutator here. But applying the anti-commutator, what produces is a minus sign in the term that is going to vanish anyhow, right? Because now we have the dagger here and this guy here, so this is 0. So the minus sign didn't make any difference. And what we get instead is eta 0, 0 acting on the times the normalization of the vacuum, or the norm of the vacuum. If we assume that is 1, which we should definitely do, then this is equal to minus 1 again. So we have negative norm states even in the fermionic oscillators. Okay? So the same thing will happen here. So I didn't tell you, but we should define the vacuum of our Hilbert space, and we will define it to be something that is annihilated by all annihilation operators, right? So if I now restrict R to be positive, this will be annihilation operators, and also by the corresponding annihilation operators of the bosonic oscillators. Okay? Very good. Now let's go back to the Ramon sector. We will find, so you see the computation is not going to be different. We will also find negative norm states. So let's not bother to discuss that. Let's instead look at the definition of the vacuum. Okay? So once again, we want the vacuum to be annihilated by all these guys. Okay? But just out of curiosity, let's look at this and set m equal to 0 and n equal to 0 in this anti-commutator. And let's see what we get. Well, we get d0 mu, d0 nu happens to be equal to eta mu nu. Well, that looks interesting, right? That looks like an algebra we recognize. So these fermionic oscillators somehow satisfy an algebra that we have seen before, or almost one that we have seen before. If we just normalize this, introducing a square root of 2, then it would actually be an algebra that we have seen before, especially if we define these objects like this. Then this algebra is nothing but Clifford algebra. So that's really surprising. We found a Clifford algebra, but it's a Clifford algebra. You would say, well, of course, there was a Clifford algebra already, but there was a Clifford algebra satisfied by the gamma matrices or the row matrices in 2 dimensions, right? We put that in by hand, right? So we had those guys sitting there because we had fermions, and we had to introduce them with the correct action. But nowhere we said that we were going to get anything that had to do with spinor representations in space-time. And somehow, all of a sudden, by just imposing these boundary conditions, we find that the D0 modes, the D0 oscillators, satisfy precisely a Clifford algebra in space-time. So that's really exciting. Imagine when people discovered this. They said, oh, so we're just one step closer to getting fermions, right? Because at least now you're seeing the correct representation. So fermions should be in what kind of representations in space-time? Spinorial representations, right? And it's hard to believe that we were going to get something in the spinorial representation if we only had mu indices, right? So we had vector indices all over the place. How can you get spinor representation from just a bunch of vector indices? So this is very exciting, that you get the Clifford algebra precisely from that. Now, the next observation is the following. At some point today, we will find the corresponding analog to the number operator in this theory, okay? But whatever this number operator is, remember, the number operator is the one that will tell us how the spectrum works. But whatever this number operator is made out of oscillators, alphas and Ds, right, in this case. And now you see, and remember, the number oscillator, the number operator, didn't have any D zeros in it. And that means that this as an operator will commute with D0. Why is that important? Well, because the vacuum, whatever the vacuum is defined so that the number operator acting on it is 0, right? And now, if D0 commutes with n, it means that whatever our vacuum is, right, it better be in a representation of this Clifford algebra. The D0s have to satisfy this Clifford algebra, and therefore, any space where they act on better fall into a representation of that algebra. So this means that our vacuum, or in fact, any state, must give us a representation of the algebra. So the surprise we find is that the vacuum is not unique, because we know that the non-trivial representations of this algebra have dimension, which is some power of 2, 2 to something, right? In fact, it's 2 to the number of entries here, or the number of possible entries here, divided by 2. If we call this D, it will have to be something of dimension 2 to the D half. Okay? So if we have many vacua, we have to give names to these vacua. Okay? So we have to give a label to the different vacua. And it seems to be convention to call it A. Well, we know we have A for the normal order ambiguity. We have A for many other things as well. One more use for A. And you will see it always inside the bracket with an R here. So that's no problem. And what does it mean that it that it furnishes a representation of the algebra? Well, that if you apply this 0 to this, what this guy does is to mix these guys, or all possible values of A, go from 1 to the half, and it mixes them precisely with the particular representation as a matrix. Okay? Well, once again, this is very exciting because this guy almost is walking like a fermion in space-time. Okay? But what else do we have to check? We only know that it walks like a fermion. Now we also have to check that something else. That it sounds like a fermion. So what else? What else do we need? The what?
The spectrum of.
Well, this is the state. So the state falls into a representation, in the correct representation. It's a spinor representation. But what else it has to satisfy? Well, that will be built into the fermionic oscillators. So that's not a problem. Yeah, so it has to propagate in space-time like a fermion, right? In order to make sure that it propagates like a fermion, what does it have to do? It has to satisfy an equation. So all we need now is a Dirac equation in space-time. Well, of course, it sounds like, oh, yeah, that's all we need, right? But where could the Dirac equation come from, right? So we have to show that this vacuum state, right, satisfies a Dirac equation. Remember, this vacuum, all these states, here and even there and in the bosonic case, they also carry an index, which I don't usually write. I think I've never written that index. What is the index that I don't usually write? No, even the bosonic ones. Even the bosonic vacuum carries an index that I don't usually write. It's a continuous index. And it's the eigenvalue.
The momentum?
Yep, the momentum. I never write momentum anywhere, but I should always, or just to be, if I really want to be rigorous everywhere, I should always write, say, in the NS sector, I should always write the vacuum. Or the more precise way would be to write where this is a momentum, right? K, or P, whatever you want to call it. So here, I should also do the same thing. And I should write the vacuum with K, right? So what would be the Dirac equation? Well, the Dirac equation would be, if this guy turns out to be massless, what should the Dirac equation be? So if massless, okay, then the Dirac equation in space-time, in momentum space, looks like this. But now this K bar means, this K slash means K mu gamma mu. Okay? That's the Dirac equation in momentum space, right? For a massless particle, for a massless spinor in space-time. Okay. So let's keep going.
Freddy,
Yes.
can you please repeat again the argument of why the vacuum states are a representation of the algebra?
Well, the argument is simply that the D0 operators commute with n, right? And therefore, they don't change the spectrum. So this means anytime you have an operator that commutes with your number operator, or in general in quantum field theory with the Hamiltonian, it means that the spectrum will be degenerate, right? And everybody in the same level will have the same eigenvalue of that operator, right? Well, in this case, we have the D0, and the D0 has to satisfy this algebra, and therefore everybody in the same sector must fall into representations of this algebra. Okay? We know that the simplest non-trivial representation of that algebra has dimension 2 to the d half, and therefore the sector with n equals to 0, so that means that the sector, well, any sector really, but the sector with n equals to 0, which is a vacuum, well, I wrote it there, must give you a representation of the algebra. Is that clear?
Why can't it be a trivial representation? If you only have one state in the eigensubspace of n, then it could just be or the zero eigensubspace of n. It could just be a trivial representation of the algebra. Like, how do we know in advance that it doesn't happen to be a trivial representation?
The Clifford algebra doesn't have a trivial representation.
Everything. Doesn't everything have a trivial representation?
Well, a trivial representation means that you put the gammas to be, what? A number.
Mm-hmm.
How can you satisfy this equation?
Only if it's a group, because it's a representation, but if it's an algebra, it doesn't.
Right? You cannot have a one-dimensional representation of this algebra, right? It will not possibly satisfy this constraint. Yes?
Why did it commute?
I didn't take it. I said that it commutes with n. N is an operator made out of alpha oscillators and d oscillators, except the 0 part, right? Remember, the 0 part is just a part that will come out from the alpha zeros. We produce a momentum, right? So the number operator, the one we define in order to define the masses, only contains the alpha oscillators with m equals to different from 0.
We did the same thing here.
And we're going to do the same thing later on today, okay? And we're going to find, therefore, that n only depends on oscillators with number different from 0. And therefore, it commutes with d0. Okay? I haven't told you what n is. That's what we want to do today, or hopefully today. Any other questions? Well, as you see, of course, the Navier-Schwarz sector will also be interesting, and we will do many things there. But really, the exciting part is if we find something like this, right? If we find something like this, we are definitely in business. This very simple-looking model will have fermions with the correct equations in space-time. And then we will only have to worry about the dimension and the way the fermions interact with. We will also have to find gauge groups and then make sure that the fermions interact with the gauge groups are charged correctly and that the theory we're going to get is chiral in 4 dimensions. But, well, those are just minor details. Right. OK. Yes?
The reason why we didn't do this in Navier-Schwarz, but was that a big problem?
Oh. So in the Navier-Schwarz sector, well, what happens here, right? Remember that the R's right? So we don't have 0, 0. So we don't have a Clifford algebra in the NS sector. So that's a very good question. So no Clifford algebra, no fermions here. So these guys will be bosons. Okay? Now, that's a very, that reminds me. So if the vacuum is a fermion, sorry, if the vacuum is in the spinor representation, now every time you apply an oscillator that has a mu index, right? So if you have this guy and you apply any number of oscillators to it, you will produce guys that are in the representation, which is a tensor product of the spinor with a bunch of vectors, right? And those guys will still produce fermions, Okay? So we not only found one fermion or one spinor, and hopefully it will be a correct thing. It will be a correct thing to do that is a physical fermion. But we also find an infinite number of them, okay? An infinite tower of them. All right. Well, let's see if we more luck here. All right. So we want to proceed with the quantization. And we have to get rid of our negative norm states. What did we do in the bosonic case? You remember, we had two choices. One was to suffer incredibly badly by trying to impose all these quadratic constraints by hand somehow. The payoff would have been that Lorentz invariance would have been manifest, right? Because the constraints and everything was Lorentz invariant. So imposing the constraints just the way they came would have preserved Lorentz invariance. But the problem was that the constraints were quadratic. So what did we do in order to avoid all the pain and just do it very easily? We did this Lycon gauge quantization in the bosonic case. Do you remember? And the trick was first to choose smart coordinates so that if we have any vector in space-time, we write it as u plus, u minus, and ui, where this I index goes from 1 up to d minus 2. And these guys were made of u0 and ud minus 1. Well, let's not put those brackets because it will look like an anti-commutator. So these two were made out of these two objects. Okay? So as if we didn't have any pluses and minuses already with the fermions, with our worldsheet fermions, we will now introduce pluses and minuses also for the space-time coordinates. Okay? So remember, we will have now psi's that will have indices which are plus and minus in space-time, and they could also be plus or minus, but the plus or minus in the psi's will represent the chirality in the worldsheet. Okay? So we have to keep track of all those pluses and minuses. Then what we did was to say, well, very good. In these coordinates, we have our bosonic action. And we said the dangerous oscillators are where? Where? They were in the x plus and in the x minus fields, right? That's where the alpha 0 oscillate, the alpha 0 but 0 upper index oscillators were hidden, right? In these two guys. How did we get rid of these guys? Can anyone give us a short summary of what we did?
We change coordinates so the x minus was only sign.
Right, so we use a residual conformal symmetry, a residual symmetry of this action, which ended up being conformal symmetry. And that was powerful enough to allow us to eat up all the oscillators of x plus, and we ended up with a formula that was something very simple. where x plus didn't have any oscillators. Then what did we do next?
Yeah, in the math formula, you solve it for alpha minus.
Well, we use the constraints, right? So now, in terms of this, the constraints linearized. Remember, what we used was this constraint. Right? Where this index, this dot, meant this contraction. But in these coordinates, this contraction means minus x prime plus times, sorry, x dot plus x prime minus this was a constraint, right? Remember, this is a big deal of the whole Lycon gauge quantization that we said we're going to avoid the pain of imposing quadratic constraints. We will make them linear. How does it happen? Well, it happens because now we look at this and we say x plus prime is 0. And x plus dot is just a number. And therefore, we can write the alpha minus oscillators in terms of only transverse oscillators, and we're done. Because now our Hilbert space is completely made out of physical objects. So from here, we concluded that the alpha minus oscillators were a function of only the alpha I oscillators. And we were done. Okay? Well, now what do we do in the fermionic case? We will have to add to this our action sorry. The same thing will happen. The dangerous oscillators will be now in psi plus and psi minus. And this is what I told you, where we are in dangerous territory with the notation, right? We have psi plus and psi minus here, but this doesn't mean the same plus and minus that we had before. In fact, if I wanted to do it fully, I could write here plus minus and plus minus here. So by this, I mean the Dirac spinors. If you want, we can write it in terms of the Weyl spinors by putting a plus and a minus here. So remember, this means chirality on the world sheet. And these indices are the mu indices in these coordinates. Okay? So let's pretend, well, say we have the same thing. Now, does this action, this plus this, does it have any symmetry that would allow us to remove some oscillators? Well, the answer is yes. It has a supersymmetric version of the conformal group. It's called the superconformal group. Okay? So in the tutorial you showed that this action has supersymmetry. It's supersymmetric invariant. And there is a super version of this group. It's called the superconformal group. And in this case, the superconformal group is powerful enough. Sorry, this is a fixed blackboard, so I won't be able to push it up. I'm going to write here, the superconformal group would allow us to set the plus oscillators or the plus minus oscillators to 0. So that's going to be great, right? Again, we only have the problems in the minus oscillators. Now, what is a constraint in this theory when we have this plus this? Well, first of all, if we just have this theory like this, and we impose just this constraint, we will have the same problem again, right? But with the minus oscillators in the fermionic part. this constraint will only allow us to get rid of the alpha minus oscillators. Here, we only get rid of the D plus or the B minus or the B plus oscillators, but we don't get rid of these guys. Okay? So this theory, just like that, doesn't make any sense. So what do we have to do? What do you think?
The energy momentum tensor has to be 0, but the new energy momentum tensor.
You say that the way we got this was by imposing that the energy momentum tensor of the theory was 0. Right, very good. So let's remember how we did that. So let's go back to the literally. We have to go back to the drawing board, right? We started with this action. We pretended that we could just add the fermions to this action and keep going. That was a little bit too cheap, okay? We really shouldn't have started from that action. We should have started one step before. Where was that? Well, we should have really started here. Right? That is a theory that we knew makes sense from the beginning. Right? That's a theory that later on we can show, or we ended up concluding that it was equivalent to our nice free theory here plus constraints. Well, now we have to add our fermions to this theory. But this theory is a quantum field theory in 2 dimensions where the space-time, the 2-dimensional space-time, has a curved metric, right? So how do we add fermions here? By using what? That's right. So I think in 2 dimensions, we can call them I think we can call them dyads, perhaps. Okay. So once again, as if we didn't have A indices, here is another one. This one goes from 0 to 1. A and B go from 0 to 1. So these are indices in the tangent space where we have our nice Lorentz group. And these are the space-time indices. Okay? Once we have this, well, we can keep this here. Well, let's write it in terms of this. And what do we have to add? Well, now we can write our fermions. So let's put our index mu and nu, eta mu nu. But what do we mean by this derivative? Well, what we mean by this derivative is the following. Is rho alpha d alpha, where these rho alphas are the gamma matrices, or the rho matrices, in the curved space. And they are related to the ones on the tangent space, again by, let's put the index down, using our dyads. And what is this covariant derivative? I didn't write a single derivative because this guy, we will have trouble acting on these spinors. Have you seen the spin connection before? Have you seen how to couple fermions to? Yes or no?
We had that on tutorial.
It was on a
Friday.
tutorial. Oh, okay.
Freddy, we had that on tutorial on Friday.
Oh, we did it in this tutorial. I see, but not before. Not in the GR courses.
Not everybody took GR courses.
Oh, not everybody took GR courses. Okay. Let's see. Well, given the time, yeah, okay. Well, you did it but review it again. The spin connection, so what we have is that this d alpha is basically this derivative. This is a covariant derivative, and this is a spin connection. Okay. Now we have this, and we say, very well, we can once again using, so remember in the bosonic case, we use Diffeos plus Weil to translate the metric to eat up all the degrees of freedoms of this guy and setting it to a flat spacetime. So we can do exactly the same thing here, and we still have to keep the equations of motion, which is the energy momentum tensor of this theory. And what is the energy momentum tensor of the theory? Well, it's the same as before, minus the trace, of course, plus fermions, plus a contribution that comes from here. Okay. However, note that if this is all we have, and we impose this as a constraint, it's basically the same equation, except that we will also have some fermionic oscillators here. But we will only be able to get rid of x minus of the x minus oscillators. We don't have any way of getting rid of the psi minus oscillators. Okay? So this is a terrible situation to be in, because I locked the two blackboards that I want to use are the fixed ones. I mean, so I cannot move them up and down. But we're running out of time too, so maybe I'll just do this here. So what's the situation now? It seems that we're in a desperate situation from all points of view, timing and blackboard situation, okay? But more importantly, we're in a desperate physical situation, right? So what is the physical situation? The constraints that we have from this theory are that this is equal to 0, and this will allow us to write x minus as a function, or x minus prime as a function of the other of the transverse directions, and this and the fermions, the transverse fermions, right? And this will only allow us to get rid of these oscillators. BIs or DIs, depending on the sector. And the situation is that nothing seems to kill the psi minus plus minus oscillators. And these guys still produce negative norm states.
But you cannot, can you relate the alphas with the other oscillator by supersymmetry?
Which ones?
The alphas with the fermionic oscillators with a super.
Very good, very good. So you would say, well, but shouldn't there be something that tells you that these guys are related to this? But remember, only this action was supersymmetric. This action was supersymmetric. Now, if we could only find supersymmetry in this action, that would be the solution to the problem. Because then the alphas and the psis would be correlated. And therefore, if we get rid of these guys, there must be the analog of this constraint, or the super version of this constraint, which will kill these oscillators. So if we could only make this thing supersymmetric, then we will be in business. Okay? Well, but here we have the x's and we have the psi's. So they are super partners of each other. That's what you proved before. But now we have these dyads here, and they are just bosonic. What can we do? Well, we have to introduce a super partner for those guys. Otherwise, we will not have supersymmetry. But you see that this is something really remarkable. The model, without anything else, cannot be made physical because of these negative norm states. But the solution is absolutely clear. What we have to do is to make this action supersymmetric in order to get rid of that. So somehow supersymmetry is imposed upon you. It's not something that you can make a choice of making this action supersymmetric. It has to be made supersymmetric. So let me write, it's a little bit complicated. So let me write what it looks like. So is that clear? We are in a desperate situation, and it calls for desperate measures, right? And then the measure is going to introduce a new field here to make this action supersymmetric. So we're going to make the action supersymmetric. And this is going to be our first supergravity. It's called supergravity because it has a gravity field in it. And we're going to introduce the superpartner. Let me remove these parentheses from here. So we have the same piece that we had before, so you shouldn't have erased that. So the new field, or the superpartner of this, is our gravitino, and the action, something that looks like this. Slightly longer than that. Okay, we're done. That is the correct action that we should use. So once again, the super version of this will allow us to get rid of the metric and the gravitino. Okay? So there will be what is called local supersymmetry. Which is exactly, or is similar to the transformations you studied before, but now where the supersymmetric parameter, epsilon, can depend on the space-time coordinate sigma. And this action will be invariant under that. Somehow the gauge field for that local supersymmetry is the gravitino. And this plus a supersymmetric version of I will be enough to set the metric to this and to set the gravitino to 0. Now you would say, well, big deal what we did. We wrote down this thing that is very complicated. Who knows who was able to find this thing? It looks very complicated. And in the end, you're going to set this to the flat space metric and the gravitino to 0. So these terms cancel. These terms vanish, right? Sorry, this is a, yeah. These terms will completely cancel. There is one gravitino here, two here, so these guys drop out. And once we do that, this action, this plus this, goes down to exactly our starting point. But why did we do all this? Because now, remember, just like we set this equal to this, and we say, well, we can do it, but we have to impose the constraint. So when we do this, we can do it, but we have to remember to set this constraint. The same thing happens to this guy. We can also do it, but we have to set the corresponding equation of motion or the corresponding field equation to 0. And the corresponding field equation only has one index. And that is called, usually people call it J. Okay? That will give us a new constraint. It is?
This is constraint because you have a term that is linear in the gravitino, in the action. So then you cannot put it to 0 in the equation of motion.
Yeah, the thing is that, yeah, that's right. So the thing is that neither the gravitino nor the metric are dynamical fields here, right? So that's why we can we can compute the equations of motions and just set them to 0. Well, the reason we have to set them to 0 is that we can use these redundancies to choose this at a particular time. But in order to make sure that these constraints stay the same as we evolve in time, we have to impose at all times the field equations that come from the variation of these guys. So that's really the source of this constraint and this constraint. But now you see that we have this one and we have this one. So what does this one look like? We will do this more carefully tomorrow, but just so that you can sleep tonight, because probably you won't be able to do it unless I tell you what happens. So let's write down what this J plus looks like, or maybe not. Oh, no, it's too late. Yeah, OK, sorry. Well, but you see that there is hope, right? This guy will get rid of the X minus oscillators. And of course, this guy will allow us to get rid of the psi minus oscillators. And then we will have our physical theory back on track. All right.